This paper is When is Amplification Necessary for Composition in Randomized Query Complexity? The authors are Shalev Ben-David, Mika Goose, Robin Kothari, and Thomas Watson. I'll explain what the paper is about by going through the title backwards, starting with query complexity. Query complexity is about decision trees, which is a model for computing Boolean functions by making adaptive queries to individual bits of the input. Here's an example of a decision tree. Each internal node is labeled with a single input variable, and then you go left or right depending on the value of that bit from the input. And which bit you query next can depend on the values of all the bits that you previously queried. And each leaf is labeled with an output. The cost measure we're interested in is the depth of the tree. So that means if the cost is low, then no matter what input we feed it, it will make few queries. The query complexity of a function is the minimum cost over all decision trees that compute the function. We're using a slightly non-standard notation here, P of f for the deterministic query complexity of f. This is because it will be convenient to recycle classical complexity class names. For example, P is the classical class corresponding to deterministic computation, and BPP is the classical class corresponding to two-sided error randomized computation. So we will use BPP of f for the randomized query complexity, and so on for other classes. So what is randomized query complexity? A randomized decision tree is just a probability distribution over deterministic decision trees. The cost measure is the maximum depth over all the trees in the support of the distribution. So if the cost is low, that guarantees that for every input and for every outcome of the randomness, only few queries will be made. Correctness means that for every input, x, the probability that the decision tree correctly outputs f of x should be at least 1 minus epsilon. And then the randomized query complexity of f is just the minimum cost of any epsilon correct randomized decision tree for f. This error probability epsilon is a subscript here, but without the subscript, the default is that we mean error probability 1/3. We're going to consider functions of a composed form. These come up often in complexity theory. Suppose we have an outer function f from n bits to 1 bit, and an inner function g from m bits to 1 bit. Then when we compose these, we'll get a function that looks like this. The input is m times n bits long. The input is a tuple of n strings, each of which has m bits. And we're using superscripts here to index the components of this tuple, because previously we used subscripts for indexing individual bits. For example, x sub I was a bit, but here x super I is an m-bit string, which is the ith component of the input. And the composed function evaluates g on each of these components and takes the resulting n bits from all those evaluations and views those as an input to f. A fundamental question we can ask about any model is, how does the complexity of a composed function depend on the complexities of f and g? We will study this question for query complexity. This is well understood in the settings of deterministic and quantum query complexity. For deterministic query complexity, the relationship is exactly multiplicative. To see the upper bound here, just note that to compute the composed function, you could just run a decision tree for f, and whenever it wants to query one of its input bits, just run the decision tree for evaluating the corresponding copy of g. And it's nearly trivial to see that this upper bound is tight for all f and g. For quantum query complexity, the relationship is known to be multiplicative within a constant factor, but that's not trivial to see. For randomized query complexity, this turns out to be quite subtle and interesting. The dependence is not so simple, and in recent years, there's been a big flurry of work on this question. We now know that for every f and g, the randomized query complexity of the composed function is at least the complexity of f times the square root of the complexity of g. And furthermore, this is essentially tight for some partial functions f and g. A partial function is allowed to be undefined on some inputs. These two results are very non-trivial. I'm omitting citations from the slide since you can find all the citations in the paper. Now, let's try to flip these quantifiers. What if we want a general upper bound that holds for all f and g, and then try to show that it's tight by proving a matching lower bound for some f and g? Well, here's a very simple upper bound we can state for all f and g. The randomized query complexity of a composed function is at most the product of the complexities times a log factor. The reason the log factor arises is because if you run a randomized decision tree for f, and whenever it makes a query, if you run a randomized decision tree to evaluate that copy of g, then the error probability could accumulate over all these different evaluations of g. So if the outer decision tree makes many queries and each query is answered incorrectly with probability 1/3, then with high probability, at least one of the outer queries may get the wrong bit. And if that happens, then all bets are off about what the outer decision tree will output. To fix this, we can just amplify the inner decision tree so that it computes g with error probability less than 1/n. Then, by a union bound, with high probability, each of the n possible outer queries would get the right bit. So then, the composed decision tree would compute the composed function correctly with high probability. To achieve this amplification for g, you could run the decision tree for g not once, but log n times, and take the majority vote. That will get the error probability down below 1/n, but it will also blow up the cost by log n factor. That's where this upper bound comes from. When is this simple upper bound tight? Well, the corresponding lower bound is certainly not true for all f and g, but it's not obvious that it's even true for some f and g. So this paper's central question is, when is the randomized query complexity of a composed function not only at least the product of the complexities, but also requires the log factor on top of that? This is the question we will study. And to formulate this question appropriately, there are a bunch of caveats which you can read all about in the paper. I'll just summarize here. We should restrict our attention to outer functions f that have linear randomized query complexity, and we should also restrict our attention to inner functions g that require a log factor in order to amplify the error down to 1/n. Not all functions g require a log factor for this amplification. And if amplifying g does not require log factor, then composing with f would not require a log factor either. Another caveat is that this lower bound with the log factor is simply not true for all partial functions g. There are some partial functions g that just never require the log factor for composition, even though they do require the log factor for amplification. So we will have to consider specific g's that have properties stronger than merely requiring a log factor for amplification. Prior work by Blaise and Brody showed that this lower bound is indeed true when f is the identity function, which just outputs all n of its input bits, and for some total function g that they designed. In this work, we focus on outer functions that just output a single bit. Namely, we'll look at these very basic functions, or, XOR, which outputs the parity of its input bits, and majority, which outputs 1 when over half the input bits are 1. A common theme when investigating composed functions in complexity theory is that if it's too challenging to consider arbitrary f and g, we can instead make progress by first focusing on some interesting specific f or specific g. That's what we're doing here. The upshot of our results is that amplification is never necessary when the outer function is OR, and it's sometimes necessary when the outer function is XOR, or majority. Theorem 1 says that for every partial function g, when you compose with OR, the randomized query complexity is at most n times the complexity of g. N here is the complexity of OR. So this is just saying you don't need that log factor if the outer function is OR. Theorem 1 is not really new, as I'll explain in a minute, but we provide a somewhat new and streamlined proof of it in the appendix. Theorem 2 shows that at least there exists a partial function g, such that composing with XOR requires the log factor. The specific g we consider here is what we call gap majority, which outputs 1 if 2/3 of the input bits are 1, and outputs 0 if 1/3 of the input bits are 1. And theorem 3 is a similar result, but for majority instead of XOR. However, the proof is considerably more involved. Some of the novelty in our theorems 2 and 3 comes from proving not just randomized query complexity lower bounds, but in fact, we get lower bounds that hold for certain models that are even more powerful than randomized query complexity. For the XOR result, we actually get a lower bound for so-called post-BPP. In this model, we have a randomized decision tree, but with high probability, it may abort, which means it gives up and doesn't output anything. And conditioned on not aborting, the output should be correct with high probability. Post stands for post-selection, which is just a fancy word for this conditioning. For the majority result, we get a lower bound for so-called WAP, which despite the exotic sounding name is actually equivalent to a simple and standard query complexity type measure. I'll say a little more about that later. Also, the proof of theorem 3 is stronger because we handle RP on the right side. RP corresponds to one-sided error randomized query complexity. Now, before elaborating on the theorems, I'll mention an important conceptual observation. The things that we're studying here are closely related to noise-tolerant decision trees. With noise-tolerant decision trees, each time the decision tree makes a query to an input bit, the query may return the wrong bit with bounded probability, at most 1/3, independently of all the other queries, including all the prior queries that you made to the same bit. There's a subtlety in defining how the adversary gets to choose the noise probabilities, but let's ignore that. We invent this notation BPP star for the noise-tolerant randomized decision tree complexity of F. This is the minimum cost of any randomized decision tree such that on every input, the output is correct with probability at least 1 minus epsilon over both sources of randomness, the tree's randomness and the random noise. There are a number of older papers studying this model. In particular, they proved that the noise-tolerant query complexity of OR is only n, so you don't need a log factor there. But for XOR and majority, you do need a log factor. Their noise-tolerant randomized decision tree complexities are n log n. And those n log n lower bounds were proved using ad hoc techniques. Now, we make an important observation. The complexity, the plain randomized query complexity of a composed function is upper bounded by the noise-tolerant complexity of F times the plain randomized query complexity of G. And the reason for this is if we run a noise-tolerant decision tree for F, we can answer each query by running a plain randomized decision tree for G on the corresponding component of the input. And the error probability for G simply becomes the noise probability for F's input bits. A consequence is that if we have a noisy upper bound for F, that implies a plain upper bound for the composed function. And the contrapositive is that if we have a plain lower bound for the composed function, that implies a noisy lower bound for F. This observation and this consequence also hold for the other measures such as post-BPP and WAP that we mentioned earlier. Now, for those older results giving noisy decision tree lower bounds, we can now see that it was not necessary to invent specialized techniques for that. We can just use standard randomized query complexity lower bound techniques applied to composed functions, and that will yield noisy lower bounds. In particular, we recover the tight, noisy lower bounds for XOR and majority but our results are formally stronger in various ways. Let me just mention a few things about Theorem 2, the XOR lower bound. There was some prior work on the noisy randomized query complexity of XOR. For the n log n lower bound, it was known to hold in the average case over a uniformly random input, and for the expected number of queries rather than the maximum possible number of queries. And our result gives all of this and more with a simpler proof. Our proof has a Fourier flavor, but it only takes about a page. Now, for Theorem 2, we knew how to prove Theorem 2 for some partial inner function, and we conjectured that a similar result ought to hold for some total inner function. That conjecture has since been confirmed. It has been proven by other authors very recently. However, they do not get a post-BPP lower bound on the left side like we do. This came out after our paper was posted, so we did not cite it in our paper, but we'll cite it here. For Theorem 3, I won't get into the proof, but I just want to quickly mention the relationship between our result and a phenomenon known as robustification of polynomials. Our lower bound holds for WAP query complexity, which is actually equivalent to something called approximate conical junta degree. Let me explain what that is by comparing to real polynomials. I'll sweep some details under the rug here, but you can think of a real polynomial as a linear combination of conjunctions. And then a conical junta is just a linear combination of conjunctions where all the coefficients have to be non-negative numbers. Prior work by Scherstoff showed that polynomials can be robustified. That is, amplification is not necessary for composition when you're dealing with low-degree polynomials. A corollary of our Theorem 3 is that in a strong sense, conical juntas are not amenable to robustification. So this non-negativity constraint on the coefficients is really inhibiting. Let's conclude with a few open problems. We know that there is a partial function g such that composing with majority requires a log factor. We showed that in our Theorem 3. But is there a total such function? That recent paper I mentioned did this for XOR, but it remains open for majority. Another open problem we'll mention concerns one-sided versus two-sided noise tolerance for total functions. Here, one-sided noise means that if the input bit is actually a 0, then you will definitely get a 0 when you query it. But if the input bit is a 1, then you could get a 0 or a 1 when you query it. Is there a total function for which the complexity under two-sided noise is strictly higher than the complexity under one-sided noise? This open problem also arose during this work. Thanks for listening.